imagine, it is redundant because it has 4 degrees of freedom, but the field, it can only contain up to 3, because at least if you generate it with mutually incoherent sources, such as fluorescent particles or stars or anything that is point sources distributed in 3D space, the field is not 4-dimensional, it has to be 3-dimensional. So this function is redundant, and that is also a very important point, because if it is redundant, it means I don't have to go to the trouble of measuring all the 4 degrees of freedom, right? Why? If they're not there, why should I measure them? At that point, please keep it in mind, it will come back again during the talk later. And of course, we're not the first ones to point it out. It has been, sort of this discussion has been around also for a long time. Okay, right. So now let's go to talk about something that I think many of you have seen in your quantum mechanics classes, and because as I mentioned, the mutual intensity function is exactly analogous to density matrices. So in order to characterize these density matrices, this fellow Eugene Wigner, he came up with a transform that now bears its name. It is called the Wigner distribution function. And that is not the reason why he won the Nobel Prize, but anyway, it was a very important development in quantum physics. And also, one thing that this thing allows you to do, even though it is not the topic of the talk today, but what this thing allows you to do is to understand very clearly the wave-particle duality in quantum mechanics, and also in optics, the duality between ray optics and wave optics. So it's a very, very powerful formalism, which sadly we do not learn early enough when we do optics. Typically, you don't learn it at all. In fact, I learned it 5 years ago when I started looking into this business. But anyway, it is very powerful, and I will tell you a little more about this function. It looks mysterious now, but I will elaborate on it a little bit, and I will tell you what it is. Okay, so this is how it is defined. So you start with a wave function in quantum mechanics, or the optical field in optics, and then you form this expression here. Please notice the integration variable is actually the displacement variable. So this is obviously a correlation kernel that we have here. The members of the product are centered at x, but we integrate with respect to the distance variable. Okay, that's very important. And the relationship to what I was talking about before, which is also goes along similar lines in quantum mechanics, is that if you take the expectation value of this of the part inside the integral, actually what you form is the mutual intensity function or the coherence function. In quantum mechanics, that would be the density matrix. Okay. And let me also say, since I made the point about whom you integrate here, you're integrating along x prime, it turns out you can also integrate with respect to the central variable. This is what I've done here, but if you do that, you do not obtain the Wigner distribution function, you obtain something else that's called the ambiguity function. And now ambiguity function, I'm sure nobody has heard of unless you're an electrical engineer doing radar systems. Radar engineers use this function a lot. It is the reason why traffic police, I'm sure in Taiwan you are subject to traffic cops, right, who use radar to measure your speed. This is why a traffic cop who is measuring your speed cannot determine your position. All right? Of course, he can see you with his eyes, but his radar, if he's going to tell you how fast you're driving, he cannot tell you where you are. Anyway, so it comes from this formulation here. And interestingly, those two, the Wigner distribution function and the ambiguity function, are related through a two-dimensional Fourier transform relationship. They are Fourier conjugate pairs. It is not obvious, but actually it's a pretty simple derivation. It takes 2 lines. All right. And then one last point to make is that even though, oops, sorry, animations are good, but sometimes if they fail. Okay, here we go. And even though this looks highly complex, right? You have complex functions, complex integrals, and so on. It turns out you can prove also quite easily that this construct here actually is a real function. It does not have an imaginary number, imaginary part, and that is not true for this one. So that's also kind of useful to remember, even though not very critical for today. So what is this? What is this integral? I'm sure many of you play music, and even more of you have seen this kind of representation. It's a musical score. It is also a time frequency representation. The horizontal axis tells you when to play a note, and the vertical axis tells you what should the frequency of the note be, right? Okay, I used to know music, I don't remember anymore, but these are basically A, B, C, the notes, right? And depending on where you put this little bean-like symbol, that tells you the frequency. So it is very similar to the phase space representation I showed before. In fact, it turns out to be identical, even though the notation, of course, that the musicians use is very different. But that's what it does. If you take this, for example, if you take this function, it is called a chirp, right? It is a sinusoid with variable frequency. If you take that and you put it into the integral that I showed before, what you get is a delta function. Is a delta function in 2 dimensions that runs along this diagonal line. So the horizontal axis is space, the vertical axis is spatial frequency, and it does what you would expect. It tells you that as you progress in the space variable, the frequency is increasing in this case, right? And of course that's very convenient because, as we know, the one-dimensional chirp function is sort of, if you generalize it into 2 dimensions, you get a spherical wave, right? So you can see why this kind of thing is interesting. It takes a rather complicated representation here and turns it into a very nice, neat, lean and compact one. All right. So let's look at this into more detail. For example, if I take a point source in an optical system and I calculate this Wigner distribution function, then what I get is a delta function that goes like this. So of course it is localized in space, and in frequency it has infinite extent, right? That's why this delta function runs, well, ideally from minus infinity to infinity. So it's a very simple result. All of these are quite easy to prove. Now, if I go to a spherical wave, it corresponds to a coordinate change, coordinate shift in the real space. In Wigner space, actually what happens is the line will rotate. And that is kind of interesting, and it can be generalized. It says that upon Fresnel propagation, the Wigner distribution actually rotates or shears. Which one happens depends on the approximations. If you use the paraxial approximation, then it is a rotation. If you are non-paraxial, then it is shear. For now, I will use the rotation approximation because the fields I will be dealing with are all paraxial, low numerical aperture. All right. Let's look at a more complicated example. This is a function that in Fourier optics we use a lot. It corresponds to a clear aperture. So it is 0 outside and 1 inside. And if you compute this Wigner distribution function, you get something like this. This is x space, this is spatial frequency. Of course, it is 0 outside the extent of the aperture. And then inside it has this rather interesting looking part. And now, if you are observant, you will see something that is slightly alarming. You see that it has a very strong positive nucleus here, but it also contains negative values. Now remember, it is real, so it does not have an imaginary part, but its real part actually can oscillate between positive and negative. Now this is alarming because in certain contexts, when you talk about wave-particle reality, it is convenient to interpret the Wigner distribution function as an energy. But it isn't quite, because energy, of course, cannot be negative, right? So that is important to remember. So in some cases, you can do that. So you can pretend that it gives you approximately, for example, here, you can pretend that it is a ray, right? So it is a ray that is in this position and this spatial frequency, and you can pretend that the quantum of the Wigner distribution within this small space is energy carried by the ray. But if you look at this position here, that would be a ray with negative energy, right? That is not very physical, but it has the benefit that it can explain diffraction. So if you balance positive and negative rays with the right way, it gives you exactly the correct results for diffraction. So it is not a physical thing anymore, it is not a physical energy, but a very useful mathematical construct. You can think about it this way, to sort of introduce negative rays in order to emulate or to rather to model wave phenomena. Now, if this is alarming to you, here is something that will reassure you. If you take an integral down the frequency axis, so you project this way, the negative parts will always be overcome by the positive parts, and you get a positive result. And now this positive result actually is the energy of the function. So if you integrate this way, you basically recover your original function in the real space. Okay, that's interesting. If you integrate along this axis, I don't know why this is happening. I think I'm moving my finger too much. Okay, if you integrate along this axis, what you recover actually, this is a mistake, it should say the Fourier transform magnitude square of the original function. And okay, so in the case of the boxcar function, this is of course a sinc square. And why is that? Well, remember what I said before, that propagation corresponds to rotation in the space. So if you start with a clear aperture at the beginning of your system, it looks like this. And if you propagate it, well, it's equivalent to rotating the axis. And it turns out that if you rotate by 90 degrees, it corresponds to propagation all the way to infinity. And of course, we know that at infinity, you get to see the magnitude of the Fourier transform of the original field. That's called Fraunhofer diffraction, right? So this result actually sort of is in agreement with Fraunhofer diffraction. So this is rather strange. I mean, one way to think about it is that you can do ray optics and still recover phenomena like Fraunhofer and Fresnel diffraction. Quite interesting. All right. And just for fun, I asked my students to do an example of this. So what you see here, this is actually from a different talk. It's some different things that I'm doing. So I will not go into the context of why this is interesting to us. But what you see is a waveguide where we have excited the third order mode. And then this structure, you can think of it kind of like a lens. It's called a Lüneburg lens. And then the field focuses. So what you see here is the electromagnetic field computed using a finite difference FTTD method. And then these two plots are the Wigner distribution functions computed at the corresponding cross sections. So this is in the waveguide, so you see it does not change very much when you go from here to there. Then the lens will do something to it, it will form this pattern. Now this is a focus ray, because it is highly localized in space and highly extended in space and frequency. And then when you let it propagate, it will start to rotate. So you can see very clearly that the relationship between this and this is a rotation. And I think you will see it better if I play a movie of that. So, okay, it will start now. So let's wait one more. So this is waveguide, lens, focus, and propagation. Again, focus when it is vertical, and then propagation later. So that's how this thing works. I kind of like these movies, so, and I have free labor from my students, so I always ask them to compute them. All right. So at this point, if I continue, my iPad will crash. So I have to temporarily get out of this, and then manually advance to the next slide. All right. Yeah, the iPad is very good for such a thing, but sometimes the movies upset it. So, all right. Okay, so let's go now on to the next topic. So I described phase space. This Wigner distribution function is an alternative name for phase space. Now let me tell you about tomography in this space. And that is sort of a very elegant topic, and I think it is very useful, even though so far it hasn't been used in practice very much. Okay, so taking the analogy to quantum mechanics a little bit further, here is the inevitable Schrödinger cut. And of course, a big part of what you do in quantum mechanics is you try to calculate evolution of wave functions, right? So let me now calculate the Wigner distribution function of Schrödinger's cut. And if I allow the time to evolve, according to the same principle I said before, what will happen? Oh, let me go back. And the analogy is that here is my rectangular aperture. This is the equivalent of the cut in optics. And then here is its Wigner distribution function. Yeah, I think this thing skipped a bit. So if you allow time to evolve, the Wigner distribution function will rotate. It won't go back, of course, this is just an animation. And then something very similar will happen to this one. If you allow the propagation distance to evolve, the Wigner distribution function will rotate. That is the idea. Now, why is this interesting? Because in quantum mechanics, if you do a measurement, it is called a quantum demolition. Basically, if you do a measurement, you destroy the phase of the wave function, and what you recover is its intensity. And it corresponds to a projection integral down the Wigner space. And so you can do this measurement at one particular time spot during the evolution, but you can also do it at different time spots as the wave function is evolving. All right? So if you do it at another time spot here, then you would actually measure the intensity of the wave function at its rotated coordinate. And something similar can happen here. If you allow the field to Fresnel propagate and you take intensity measurement, it is equivalent to taking integrals down this axis in the Wigner space. And if further, if you do that while the field is propagating at different distances, then you take measurements of rotated versions of this Wigner distribution function. Now, this sounds rather elaborate and complicated, but suggests a very simple kind of measurement. Let's say that I do this. I have now the field, I will assume it is partially coherent. In quantum mechanics, you would say that you have a superposition of states, right? You can kind of think of it that way. In optics, we call it partially coherent. And it suggests the following measurement. I can take the camera, I can put it, no optics here, no lenses, nothing. Just put the camera downstream the optical axis and measure the intensity. Can I measure the coherence of the field? No, because it is lost. All I can measure is intensity. However, I can move the camera to another position, I can take one more intensity. And then I can move it again and take one more, and so on and so forth. I can do it many, many times, right? Okay. If I do that, what is happening in these spaces that I said before? Well, let's say that this is the mutual intensity function of the partially coherent field. As I mentioned, this function describes the partially coherent field itself. It's like the density matrix. If I can measure it, then I know everything about the state of this field. Right. So, I'm not interested in that. This is what I'm sorry. I am interested in that, but I cannot do anything because I do not know it, right? What I'm trying to do is figure out how to measure that. Well, let's go to Wigner space. If I consider my first measurement, which I do at the initial position, I'm taking integrals projected downstream the optical axis. When I take the second measurement, what has happened is the field has propagated, therefore the mutual function has rotated, and therefore now I'm taking integrals that are rotated with respect to the original one. These are called projections, and this now begins to look very similar to tomography, all right? If any of you had the misfortune of having to do tomography in order to cope with some, medical condition, you know what they do, right? They put you in a machine, and then they rotate an X-ray or a magnet or whatever, and they take measurements from different angles. This is what we're doing here, but it is not a physical object that we're doing tomography. We're doing tomography in this kind of crazy Wigner space. Okay, now let's take it further. Okay. Remember I mentioned if you Fourier transform this two-dimensional function, what you actually get is the ambiguity function. The two form a Fourier pair. So what is this measurement now? This projection that I take in ambiguity space, there's a theorem, it is called the projection slice theorem, which says that if you take this measurement, the projection, and you Fourier transform it, what you get actually is a line in ambiguity space. And of course, if you do the same thing for the rotating projection, this line will also project. This line will also rotate. So each one of those measurements that I do, what I'm really doing is I'm measuring the ambiguity function along these particular orientations. And of course, ideally, what I should do is I should repeat in every different position all the way around 360 degrees, And if I do that, then I can measure the ambiguity function. If I know that, then I know everything, because I can Fourier transform it back. This will give me the Wigner distribution function, and I'm done. I've done my job, right? Okay. The problem is that, oh, and by the way, this has been done in quantum, quantum optics. This one is in cold matter, Bose-Einstein condensers, and you can see very beautiful pictures here of the matter waves, or some sort of coherent superposition of matter waves. These references are very entertaining to read. And it has also been done for X-rays. So this is another experiment fairly recent where people actually use this technique to measure the Wigner distribution function, and from that to measure the density matrix or the coherence function. The problem that we dealt with, and is sort of what I'm trying to show here, is that when you do this kind of measurement, you actually cannot fill up the entire ambiguity space. There's a lot of space that remains uncovered because either you are too close to the object or too far. All right? And because of sort of these practical limitations, you can only take these projections. It gets actually worse because if you think about it, the rotation can only be positive or counterclockwise. You cannot do negative angles, because negative angles means that you actually have to go past the object backwards. You cannot do that. And nevertheless, so when you do the measurement, these spaces are also missing. But anyway, we can kind of make up for these missing spaces by making kind of like a time reversal assumption, that when you go backwards behind the object, what you will see is the conjugate of these guys. So that is sort of easy to get around. What is still difficult to get around is what to do with these big missing cones over here. So that actually, we're coming now to the kind of the second topic of the talk, which is how you can make up for limited data. Anytime that you have this sort of limited samples, you can either give up and say, well, I cannot do it, or you can do this class of techniques that is known as compressive imaging, and I will talk about it for the next few minutes. Have about 15 more minutes? Or? All right, so let me talk about that a little bit. So compressive imaging, I'll show you an example instead of going through the math. Let's say that you want to measure this signal. This has a total length of 64 samples, and as you can see, only 3 of them are non-zero. So if you follow measurement theory, it will tell you that you really have to take all the 64 measurements, right? But this looks like a waste, because when you do the measurements, the expectation value for most of them is 0. Why should you bother to measure all? Well, because you cannot do anything else, right? But actually you can. What you can do instead is the following. Let's suppose that you can do a physical transformation that allows you, instead of measuring the signal in its native space over here, let's say that it allows you to measure it in the Fourier space. So what you see now here is the discrete Fourier transform of this signal. It looks very messy, but it is not really. This signal will produce 3 sinusoids, right, in Fourier space. So what you see here is the coherent, is the beat, basically, the coherent beat between 3 sinusoids. And now, here comes the magic. Let me take, again, classical theory will tell you that you have to measure all 64 samples, and then indeed, if you measure all 64, then you can go perfectly back into this space. But what I'm going to do, I'm going to take only 12. So those, and I choose them at random. So here they are. The red dots corresponded to 12 out of 64 measurements. The other ones, I throw them away. I do not measure them at all. All right. So obviously now this measurement is underdetermined because I have 12 measurements and I'm trying to figure out 64 positions. And the standard way of doing this kind of underdetermined measurement is to minimize the norm, the L2 norm of the signal. This is called the Tikhonov regularizer. It is used very commonly and it fails. If you try to do it this way, you recover this one, which of course looks nothing like the original signal. So no wonder it's not working, right? But recently, about I guess 2005, so I guess 9 years ago, maybe 10 by now, a bunch of mathematicians, they came up with the idea, instead of minimizing the L2 norm, what they do is they minimize the L1 norm. This is the only difference in the two formulas. Okay, you cannot see the other one anymore, but the only difference is this index here. It is the L1 norm. And if you do that, actually, magically, you reconstruct the signal perfectly. Now, there is mathematical proofs that actually show why this happens. The mathematical proofs to someone like me, they still look like magic because they have a lot of inequalities and stuff that they don't understand. But there is a simple explanation for why this works. So, now this is really simple, but actually it captures quite a bit of the actual proof of these theorems. Let's say that you have a two-dimensional space, and you're trying to find the solution in this space, but you only have one measurement. And this measurement is linear, very important. Right? So if it's a linear measurement, it will actually give you a line in this two-dimensional space, but you don't know where the solution is in that line. It can be anywhere on that line, correct? Now, the standard way to use L2, it will tell you that you have to minimize the energy of the solution. Minimize the energy means I have to find the point on the line that corresponds to the sphere with minimum radius. So the solution is here, and as you can see, it does minimize the energy, but it is not sparse. It is, its components are both non-zero, right? This point here has a non-zero x-coordinate and non-zero y-coordinate. So it is not sparse. It does not look like the signal I showed before that is zero everywhere with very few non-zero spikes. On the other hand, let me try to minimize L1. If I try to minimize L1, the minimum L1 energy surfaces, they look like diamonds. And you can see that the diamond actually will beat the line onto one of the axes. So if I do this kind of minimization, then the solutions that I tend to produce, they will look like this. They will have a lot of zeros, one or a few non-zero elements in high dimensions, and all zeros again. And now this is what the solution that we call sparse. So you can see sort of very intuitively why these techniques work with L1 metric, but they do not quite work with L2. So what I will, this sort of tells you that you cannot push this too far, because, so here is the number of non-zero samples versus the total number of Nyquist samples, and then you can see that your probability of success will fail if the number of samples exceeds some limit. So basically this is the criterion for sparsity. As long as the number of non-zero samples is less than this particular limit, then you can actually recover it with very few measurements. That is the idea. That is the idea of this technique. And this paper is actually very understandable, so you can read it if you like to learn more about this. So now let me show you how we use this idea in order to recover the sort of density matrix or the correlation function in our experiment. So this movie went too fast, so we'll play it again. This is our experimental setup. It is a light source. We control the coherence by using a slit. And then this is sort of an object that we're trying to measure. So basically the idea, what we'll try to do, is we want to recover the correlation function inside this space over here for a partially coherent field. And what we'll do, as I mentioned before, is we have a camera and we'll move it backwards and we'll capture images. So the movie that you see here, and we'll play it again, what it shows you is a cross-section of the images as a function of z. So, okay. So as you move the camera, this is the intensity pattern that you record. All right, and to put it in context with the previous one, this is the structure of the ambiguity space in our particular experiment, and you can see that we're missing a pretty big part of it. 38 plus 22 degrees, 60 degrees, so whatever it is, I think we're missing about 2/3 or 3/4 of it, something like that. All right. So, first of all, this experiment was very carefully calibrated because we wanted to know if what we're recovering is correct. So we used the approach